Hey everyone. So last time I introduced the fundamental duality theorem briefly, and the weak duality states that in the symmetric primal dual pair, okay, first of all, let me share my screen. And just keep forgetting. Sharing my screen. So, okay. So here's our slide. Okay, so this is the one. Okay, so the first one, the weak duality property states that in the symmetric primal dual pair, the CX. So the CX is right here, right? Which is from the optimal objective function value to the primal minimization problem, right? So this value CX is bounded from below by BY here. And BY is from the dual or the optimal objective function value, right? So which is referred to the weak duality, right? Also, as we make these bounds increasingly tighter, the lower bound becomes exactly the same value as the primal optimal objective function value. So that is what is called the strong duality, okay? Right here. And the strong duality theorem is very important because it indicates that we can solve the dual LP in place of the primary LP, a lot of cases, right? And also the second case, if one of the problems has the feasible solutions and an unbounded objective function, which means it has no optimal solution, right? Then the other side of the problem in the symmetric primal dual pair has no feasible solution, okay? And from the third and fourth, I believe we can also say that if one problem has no feasible solution in the symmetric primal dual pair, then the other problem has either no feasible solutions or an unbounded objective function values, okay? Excuse me. Okay, so okay, so today we are going to talk about the complementary Slangness theorem. Okay, so these are the complementary Slangness conditions. Okay, and again here we consider the symmetric primal dual pair. So if we suppose the x hat and y hat, actually here to distinguish, I'm going to put the hat both here. So if we suppose x hat and y hat are feasible solutions to the primal and dual problems, respectively, sorry, then they are each optimal in their respective problems, okay? If and only if these complementary Slangness conditions hold, okay? For both the primal and dual problems. And the complementary Slangness conditions say that whenever the constraint of one problem is slack. Okay. So this means that the constraint is non-binding constraint. So earlier when we talk about the graphical method, we talked about binding constraint and non-binding constraint, right? So here it does say whenever a constraint of one problem is slack, that means that constraint is non-binding constraint. So that the constraint is satisfied with strict inequality, okay? Then the corresponding variable of the other problem must be 0, okay? That's one of the complementary Slangness condition, okay? And the complementary Slangness condition also say that whenever a variable of one problem is non-zero, actually is positive, okay? Then the corresponding constraint of the other problem is tight, okay? So here, tight. So which means that the constraint must be satisfied with equality, okay? So actually the what is that? The strong duality theorem implies that the complementary Slangness conditions must hold for both the primer and dual LPs in the symmetrical primer dual pair, of course. And the converse of this also is true. And if the complementary Slangness conditions hold for both primer and dual problems, then the strong duality theorem also holds. Okay, so if you want to know more about this feature, then you can find more detailed information from our textbook. So I do highly recommend you to read our textbook on that. Okay, so basically, I do say the complementary Slangness theorem talks about the necessary condition or even the sufficient condition for both X hat and Y hat being optimal for both primer and dual LP in this symmetric primer dual pair. Okay. Okay, so now let me give you some examples for the complementary Slangness theorem. Okay, so this is the first example problem. So with this example, first we'd like to construct the dual problem and then find its optimal solution. And then use the complementary Slangness theorem and the optimal solution for the dual problem to find the optimal solution for the primer problem. Okay, so that's what you're going to do. So let me split the screen in half. Okay, should be okay, right? Just a little bit. Okay, and okay, let me open MS Word file. And let me disable my screen, my camera for a while. Okay, so okay, so let's construct the dual problem first. And since the given problem is maximization problem with or less than equal constraint, right? And the decision variables, both decision variables has non-negativity restriction. So that's the dual LP in the standard symmetric primal dual pair, right? So the dual must be minimization problem with greater than equal constraint, right? So the dual must be minimization problem with greater than equal constraint. I'm going to put right here. Okay. So if I want to use y variable as the dual variable, then I'm going to have y1. Because the primary system is 1/2, right? It has only one constraint and two decision variable. So it's 1/2 system. So dual must be 2/1, right? So I'm gonna need to write down y1 twice. In both cases, that's greater than equal sign. And here, objective coefficient vector 2, -4 serves as the right-hand side vector of the dual system. So we have 2, -4, right? And the right-hand side value, 1, becomes the objective coefficient value in the dual system, right? So we have 1 here. And here, 1, -1 becomes 1, -1, right? And the dual variable also has to be greater than equal to 0. So this is the dual LP given this primal LP. So that is very simple, straightforward, right? And we know that if we multiply -1 on both sides for the second constraint, then it's going to be y1 must be less than equal to 4, right? So from here, from these two constraints, we know that y1 has to be greater than equal to 2, or less than equal to 4, right? So it's very easy to see that y1 equals 2, where the lower bound of the variable y1 has to be 2, right? And y1 equals 2 does satisfy both constraints with sign restriction here. So y1 equals 2 must be the optimal solution for this dual LP, right? So I'm going to put y1 equals 2, and I'm going to put asterisk, indicating this is the optimal value, okay? So dual optimal objective function value, so let me set equal to W, okay? Then this is also going to be our dual optimal objective function value, W, okay? Okay, so we've done the first part A, okay? So we found the optimal solution by inspection. Now we are going to use the complementary Slangness theorem and the optimal solution from this dual problem to find the optimal solution for the primal problem, okay? Okay, so let's go back to the screen that shows the complementary Slangness theorem, which is right here, okay? So we're gonna stick to these complementary Slangness conditions, right? There are two of these, okay? So we are going to investigate these two conditions one by one, okay? So by complementary Slangness condition, it does say whenever a constraint of one problem is slack, then the corresponding variable of the other problem is 0, right? So here, considering the dual objective, dual optimal solution value. Okay. So at the dual optimal point, which is y1 equals 2. So let me write down here, at the dual optimal point, y1 equals 2. We need to see which of these dual constraints are non-binding constraints. Here, slack means non-binding constraint, okay? So we want to see at this dual optimal point, which of these constraints are non-binding, okay? So which constraints are non-binding constraints? This second one, right? This is the non-binding constraint, right? Because this dual optimal point is on this line, right? But there is a positive gap between this line and this dual optimal point. So this must be non-binding constraint. At the dual optimum. Okay, so again, so considering this first complementary Slangness conditions, we identified at this dual optimal point, the second constraint is non-binding constraint, okay, at the dual optimum, which means that this is the second, right, constraint. Then the corresponding variable. What is the corresponding variable? That means second primal variable, okay, must be equal to 0, okay? The value of the second primal variable must be 0, okay? So what is the second primal variable? That's going to be x2, okay? So x2 must be equal to 0, okay? From this first complementary Slangness condition, okay? From the first complementary Slangness condition, we can obtain this important result, okay? Okay, now let's consider the second complementary Slangness condition. So it does say whenever a variable of one problem is positive, then the corresponding constraint of the other problem is tight, okay? So at the dual optimum, at the dual optimal point, again, at this point. The dual variable, actually, we have only one dual variable, which is y1, right? At this optimal point, this dual variable has a positive value of 2, right? So it has positive value. So according to the second complementary Slangness condition, the corresponding constraint of the other problem. So it does say this is the first dual variable has positive value. So the first primal constraint must be tight constraint, which means the first primary constraint must be equality constraint, okay? Must be equation. Equality constraint, okay? So if we go back to the original problem here, to say the first primary constraint. Actually, in the primary system, we have only one constraint, right? So this primary constraint, x1 minus x2, must be equal to 1, because it does say it must be equality constraint, right? So instead of less than equal sign, we're going to use equality sign here, okay? So from the complementary Slangness theorem, we obtain these two important information, okay? So if you plug in these two to our original primal system, then you should be able to get the primal optimal solution, okay? Right? It's very easy. Since x2 value is 0, so this is 0. That means x1 must be equal to 1, right? So x1 must be equal to 1. And x2 equals 0. So these are the primal optimal solution, okay? And so our primal optimal objective function value must be equal to 2 times 1 plus minus 4 times 0, right? Which is equal to 2, okay? So what can you say from this result? These two objective function values, right? One from primal, one from dual. These two values are equal, right? Which is about strong duality. Is that right? Okay. So let's move on to the next example problem. So this is going to be very similar to the previous one. Let me just add more. Fine. Okay, it doesn't matter. Okay, so I'm going to use. Okay, so this is our second example problem. Again, the very first step is to construct the dual LP and then find its optimal solution by inspection. After that, using the complementary Slangness theorem and the dual optimal solution to find the primal optimal solution. That's what you're going to do. Excuse me. Oh, it's very dry here. So, okay. So the given LP is the minimization problem with greater than equal sign, right? So that is the primal problem in the symmetric primal dual pair, right? So the dual must be maximization problem with less than equal constraint, right? Okay. So in our case, the dual must be max and it's going to be less than equal constraint, right? The primal problem is 1 by 2. It has only one constraint and 2 decision variable. So dual must be 2 by 1, right? Which means it has 2 constraints and only one single dual variable, right? So let's use y variable as the dual variable. Then again, 10, 5 from the objective coefficient in the primary system, and 50 becomes our objective coefficient value. Okay, this is 50. Sorry. And our constraint coefficient should be 5, 3 in order, right? And y variable also has to be greater than equal to 0, okay? Okay, so this is the dual LP. Now, let's identify the dual optimal solution by inspection, because it has only 2 constraints and only one dual variable. So it's very easy to find, identify its optimum. Okay, so this can be rewritten as y1 is less than equal to 2, right? How about this? y1 is less than equal to 5 over 3, okay? So we know that the first constraint is redundant, right? So we just need this one, right? So because the dual optimum is maximizing 50 times y1, right? So the dual objective function value will be improved if this y1 variable increased, right? And from this constraint, we know that y1 equals 5/3 would be the upper bound of this y1 variable, right? So we may conclude that y1 equals 5/3 would be the dual optimal solution, right? And the corresponding dual objective function value, W, would be 50 times 5/3. That's going to be 250 over 3, right? So that's our dual optimal objective function value. Now we're going to use the complementary Slanginess theorem. And this dual optimal solution to find the primal optimal solution. Okay. So let me bring in the complementary Slanginess theorem. Okay. Here. Okay, so the first complementary Slanginess condition says whenever a constraint of one problem is slack or non-binding, then the corresponding variable of the other problem must be 0. Okay. So at the dual optimal point, so at the dual optimal point, which is 5. No, what is that? 5/3. Pretty strong. Okay, 5/3. Okay, so this dual optimal point, the only dual variable, again, this is y1, has positive value, right? Sorry, we are talking about the first condition, right? Not the second condition. So at this dual optimal point, we want to see which of these dual constraints are non-binding constraint. This one, first constraint, right? Because it is easy to see that if you just plug in this value to each of these constraints, then y, which is 5/3, 5 times 5/3, which is 25/3, is less than equals 10. How about the second one? 3 times 5/3. How much is that? It's 5, right? Is less than equal to 5? Actually, 5 is equal to 5, right? But this value, 25/3, is definitely less than 10, right? So this must be the non-binding constraint, and this must be the binding constraint at this dual optimum, okay? So we notice that at this dual optimum, the first dual constraint is non-binding, okay? So according to the first complementary Slanginess condition, no, let me just delete this. Okay. Then the corresponding variable of the other problem. So the first primal variable must be 0, okay? Which means x1 value must be equal to 0, okay? That's what you can get from this first complementary Slangness condition, okay? And if you look at the second condition, it does say whenever a variable of one problem has positive value, then the corresponding constraint of the other problem must be equation, okay, is tight. So again, at this dual optimal point, the only dual variable that we have has a positive value of 5/3, right? Which means the corresponding primal constraint must be equation. Okay, so we have only one primal constraint. So 5x1 plus 3x2 must be equal to 50. Okay, so these are two very important information that you've got from the complementary Slangness theorem. So if you plug in here, then this part becomes 0, and then x2 must be equal to 50 over 3. Okay, that's going to be the primal optimal solutions. Okay, then the corresponding primal optimal objective function value must be equal to 10 times 0, which is 0, 5 times 50 over 3. So it's going to be 250 over 3. Okay. Again, if you look at this, we have identical values, right? Here. So again, this result agrees the strong duality. Does that make sense? Okay, so now let's move on to the next example. Okay, so the next example problem is like this. So let me put, okay, number 3. And I'm gonna insert another page, blank page. Okay. Okay, so again, given this primal LP, we need to construct dual LP and find this optimal solution. And then using the complementary Slangness theorem and the dual optimal solution to find the primal optimal solution. Okay, that's what you're going to do. So the given LP is maximization problem with all less than equal constraint. The dual must be minimization problem with all greater than equal constraint, right? And because the primary LP is 2 by 2, right? Our dual LP must be 2 by 2 as well. Okay, so I'm going to use y1 and y2 as the dual variable. And I'm going to write down this twice. Yes, we are going to have 2 dual constraints, right? And 5, 2 becomes our right-hand side values, and 3, 10 becomes our objective coefficient, and 1, 1 here, and 0, 1. So we don't have y1. Okay. Okay, so that's our dual. of course, both dual variables, y1 and y2, must be greater than equal to 0. So that's our dual LP. Okay. Now we want to identify the dual optimal. So let's use the graphical method. It's going to be easy. As usual, we're going to use y1 axis, the horizontal axis, y2 as the vertical axis. Okay. And from the second constraint, we have let's say this is 2. The feasible region should be this side, right? And the first constraint is going to be 4, 5, maybe right here, somewhere around. And also we have, let's say around 5 here. Then we're going to have cross this line like this, okay? And because the origin does satisfy, no, the origin does not satisfy this, right? First constraint, 0 plus 0 is not greater than equal to 5. So 0, this origin cannot be the feasible point when you consider the first constraint, which means the feasible region should be this side, right? So our feasible region should be here, okay? And the ISO value line is going to be, let me, how to change the color. Okay, right here. I'm going to change the color. So our ISO value line should be something, where is that? How come? I cannot change the color. Let me see. Let me stop the video and let me figure it out and come back. Okay, now I figured out how to change the color of this pen. So, okay, so our ISO value line at this point, 0, 5, would be something like this, okay? And if we move the ISO value line in this direction, so both y1 and y2 value will be decreased. In a way, we can get the minimum value of this, right? So we're going to move ISO value line this direction. Then you will see that this is going to be your optimal point, right? Because that's going to be the last ISO value line touching the feasible region or intersecting the feasible region, okay? So how do you get this optimal point? You just need to solve these two equations, these two binding constraints. Actually, at the dual optimum value, both constraints are binding constraints, okay? So here, y1 plus y2 equals 5, and second constraint, y2 equals 2. You just need to solve this. Since we know y2 is 2, y1 should be 3, right? So y1 is equal to 3, and y2 equals 2. That's our dual optimum point, right? And the corresponding dual optimal objective function value, W would be 3 times 3, which is 9, plus 10 times 2, which is 20. So it's 29. It's going to be our dual optimal objective function value. Is that right? Okay, now let's use the complementary Slangness theorem as we did before. So at this dual optimal point, which constraints are non-binding? So at this dual optimal point, both constraints are non-binding, right? So none of the dual constraints are non-binding. So from the first complementary Slangness theorem, we don't get any information, okay? And what about the second complementary Slangness theorem then? At this dual optimal point, which variable has a positive value? Y1 or Y2? Both, right? Both dual variable has positive values, right? 3 and 2. Is that right? Which implies that the corresponding constraint of the other problem must be tight, which means both of these primary constraints must be equation. So y1 must be equal to 3 and y1 plus y2, I'm sorry, x1 equals 3 and x1 plus x2 must be equal to 10, right? So that's going to be our primal optimal solutions, right? So I'm going to put asterisk here. So x1 is 3, so x2 must be equal to 7. So x2 must be equal to 7, right? And the corresponding primal optimal objective function value is equal to 5 times 3, which is 15, plus 2 times 7, which is 14, right? It's going to be 29. Does that make sense? So again, the dual optimal objective function value and the primal optimal objective function values are equal, okay? That does support the strong duality. Okay, so let's move on to the last example for today. Okay, so this is going to be the fourth example, and I'm gonna insert another page. Oh. Let me just open the new file. Oh, what happened? Okay, let me delete this and then come back. Okay, so this is our fourth example for today. So again, given this LP, we are going to construct a dual LP and find its optimal solution. And after that, using the complementary Slangness theorem, the dual optimal solution, we are going to identify the primal optimal solution. Okay, so Again, the given LP is maximization problem with all less than equal constraint, right? And all of the decision variables are greater than equal to 0. So this is a dual in the symmetric primal dual pair. So our dual problem must be the minimization problem with all greater than equal sign. And our primal problem has 2 constraints and 3 decision variables. So it's 2 by 3. So our dual must be 3 by 2 system, right? And it's going to be minimization problem, right? And the primal right-hand side values becomes our dual objective coefficient. So it's going to be 30 y1 plus 40 y2. That's set equal to W, our dual objective function value. Subject to, we're going to have 3 constraints, right? So I'm going to write it down y1, y2, 3 times. And constraint coefficient, 1 becomes here, first constraint coefficient, and then 5, negative 5. So we have 5, negative 5, right? And here 2, negative 6. So we have 2, negative 6. So left-hand side of each constraint in the dual system is done. And the primal objective coefficient values, 5, 2, 3 becomes the right-hand side values, the dual system in order. And it's all gonna be greater than equal sign, right? Because it does follow the standard format, right? The given LP is the dual problem in this symmetric primal dual pair. And both dual variable must be greater than equal to 0, right? Okay, so this is our dual problem, okay? Okay. Now I'm going to use the graphical method again. So let me change the color of my pen. Did I do this? Okay, here, the format. So I'm going to choose blue. Okay, so we have vertical axis, which is y2 axis, and then y1 axis. Yeah, we have the origin here. Okay, and we have 3 constraints, right? Okay, so first of all, let's rewrite down all of these constraints to our constraint. Okay, so the first constraint would be y2 is greater than equal to negative y1 plus 5. So our first constraint. Second constraint would be, I'm going to move y2 term to the right-hand side. Then it's going to be, and then divided by 5, right? Or just simply, let's divide by negative 5 and then move y1 term to the other side. So you're going to have y2 here, and it's got to be less than equal sign, and y1 minus 2/5, right? That's our second constraint. And the third one, let's divide by -6 and move y1 term to the other side. So that's going to be y2 and less than equals 1/3 y1 minus 1/2. Right? That's our third constraint. Okay, so simply this is going to be our first constraint. So this is going to be 5 and then 5, right? And our second constraint would be something like this. So this is going to be -2/5, right? So that's our second constraint. And what about the third constraint? So let's say this is -1/2. Then something like this. That's our third constraint. Okay. So let's identify the feasible reason. What is the feasible reason? So the origin doesn't satisfy this, right? The feasible reason should be this side, right? How about this? This origin does satisfy this? No. How about this? Origin doesn't satisfy this. So the origin cannot be the feasible reason. The feasible reason should be this side and this side. So where do we have the feasible reason? Feasible reason should be this area. Okay, those are the feasible reason. I'm going to use red to draw the isovalue line. Okay. The isovalue line should be something like this. Okay. So it's less steep compared to the slope of the first constraint. And we want to minimize the objective function. So you want to move the isovalue line in this direction. Okay? Then you will see that the last isovalue line that touching the feasible region should be this, right? So our optimal point should be here. Okay, so it's very easy to see that y1 prime, y2 prime, our dual objective function, dual optimal solution should be 5, 0. Okay, and the corresponding dual optimal objective function value, W, gonna be, it's gonna be 150, right? Okay. Okay, now let's use the complementary Slangness theorem. Okay, yeah. So this dual optimal point here Which constraint are non-binding constraint? So it's very easy to see graphically at this dual optimal point. The first constraint is binding constraint, and both second and third constraint are non-binding, right? So here at this dual optimal point, second and third dual constraint are non-binding, right? This implies that the corresponding variable of the other problem, so the second and third primary variable must be equal to 0. So we can see that x2, x3 must be equal to 0. Okay? And the second complementary Slangness condition says that at this dual optimal point, which variables are positive? You see this? Only the first dual variable has positive value, right? So the first dual variable has positive value. This implies that the corresponding constraint of the other problem, so first primer constraint must be equation, must be equality constraint. Okay, so if we go back to the primer LP, then from the second condition, it does say that this constraint x1 minus 5x2 minus 6x3 must be equal to 40, okay? And we know that both variables x2, x3 are equal to 0. So this part is 0, this part is 0, okay? So we know that x1 must be equal to 40. So x1 must be equal to 40, okay? Since x1 has the positive value, right, of 40, and the other two primary variables, x2, x3 has 0 value. So here from the primer optimal, primer objective function value of g gonna be 40 times 5. How come? It's 200. Oh, I see. I made a mistake. Although I told you the first primary constraint is equation, actually what I used is the second primary constraint. So it's going to be 30, right? We have to use the first constraint. So that means x1 value must be equal to 30, okay? So 5 times 30 is going to be 150. Either way, the primer optimal objective function value is equal to the primer is equal to the dual optimal objective function value of 150. Okay. Again, this support the strong duality. Okay. Okay. Sorry to make you confused, but so that's it for today. So I believe this is our last time talking about the duality. So from next time, we are going to move on to the new topic. But I believe later this semester, we're going to come back to this duality, especially when we talk about the project scheduling problems. Okay. Okay, thank you very much. I will see you next time. Bye-bye.